What I want to do today, I want to tell you today how you can look at this diffusion process from a variational inference point of view, right? And all of those troubles we went through in the previous chapter is going to pay off today because you do know what is variational inference, what is ELBO, and you don't going to get so hard through the mathematical details. So you can look at the problem from this point of view as well, and why we need it, I'm going to explain it briefly. But the big picture is that this diffusion idea is interesting, but when you start playing around with it, at some point you see that it is extremely limited in terms of replicating your data distribution. The main reasons I'm going to show you. And because of that, people thought, OK, it's not going to work. They gave it up, right? But a few people kept on working on it, and at some point they started to see that, OK, you eventually don't need to really think you are going to mimic exactly the physical diffusion process. You can think of it as statistical diffusion process. And then you really need to make the final back or reverse diffusion to look like your data distribution. This is, again, one maximum likelihood problem. You're going to do the maximum likelihood. You cannot do it explicitly. You do it implicitly by variational inference. And then after that, you're going to get one expression, which is quite intuitive and leads to what we nowadays have as DPM or DDPM. OK? Everybody's cool? So this is what I'm going to do today. And let me start with just give you a quick overview why, if you keep on insisting on this approach that we did in the last two sessions, this is not going to end as perfect as you want. So this approach is what I call it approximative approach. The main reason is that, say I want to, just remember what we did last time. So the thing was that we were looking at the SDE. The SDE was described in a continuous time, right? And then we just came up with one approximation, right? Now what I'm going to do from now on, I'm going to just write down this time t here as an index. And this time t is not really the continuous time that you had before, because quickly today we are going to start working with those approximations. So xt is eventually something like I that we had before. So it's a discrete time. So every xt is, you can think of it as the location of your particle at one particular time, right? And these times are in physical time domain really close to each other, right? So if you write down the SDE and then you just use the approximation, which we used the other sessions, you end up with this expression if you assume that this is your drift term, right? This is the one which we started to just develop the whole model we had in the last session, right? And to just make sure that the variance is preserved, then we just made this diffusion term in terms of beta in a form that this happens, right? So when you are moving just a tiny bit in time, then the new process still has the same variance, right? But the variance of noise is higher, the variance of the data is getting lower, right? Cool? So that was the thing that we did, and we wrote it down in this form. So the other session, I showed you those, alpha and alpha bar, and that was cool because I needed to have that dashed line, forward and backward. Now that I don't need it anymore, I'm going to show it in this standard form, and this is the one which people use usually in the papers and other surveys on diffusion models, so it's better that we stick to this one. So this alpha t is eventually that 1 minus beta t dt, right? You have seen it, but you don't need to think about it anymore, right? So alpha t is some number which is very close to 1, and this 1 minus alpha t is eventually something very tiny, very close to 0, right? So you always have something like this. Again, you see that if you just compute the variance of this term. Assuming that you start from unit variance sample, then it's going to be again 1. So every time you're going to keep the variance to be 1, right? So, and this epsilon t is independent Gaussian process, zero mean unit variance. This is the one which we had in the SDE, right? When we approximate the SDE, we're going to get this one. Now, the point was that we started from data, x0, that is a data sample, and every time we go to a new process, right, till we end up with xt, which is eventually completely noise. And every single of those steps is described by that beta inside the SDE, right, which for us now is just representing alpha, right? Okay. For us, this is representing alpha, right? Okay. Now, key observation here, beta is the only thing that you need to describe your forward pass, right? Or forward, diffusion here. And this is the one which is going to take us from data to the noise, right? Now, when we want to move backward, what we do, we just try to write down the reverse SDE, right? So the reverse SDE is going to tell us how we can get back from xt to x0, right? And again, that reverse SDE, when you write it down, every single step, it needs exactly the beta of that step, right? Meaning that it's going to need exactly the alpha in your equation of that step, right? So if you know what is the alpha that you moved your first step, second step toward the last step, then you eventually know how to move backward using the reverse SDE, right? So this is what we did last time. Okay, cool. So one key point here that we talked about quite a couple of times last time is that, I mean, last time I showed you this x0 to be like x0 forward, right? x1 forward and so on. Then we get here, then we have backward things, right? I wanted that one because I wanted to indicate that this xt and this xt, they are not necessarily the same thing, right? You remember this, right? So I'm not showing it anymore because I don't want to confuse you further with too much notation. But you do know that, for example, this particular xt here and this xt, they are not the same thing, right? They are different things because they are coming from random process. But if we can exactly move on the reverse trajectory, on the reverse diffusion, then they are going to have exactly the same distribution, right? And this was the whole key point, right? We start from data, we get to noise, then from noise, we keep on going backward till we get into one sample whose distribution is distribution of data, meaning that we are having a new data sample, right? Cool? Okay, so that was the idea. Now, if you wanted to just write down the reverse trajectory, you can go ahead and do the calculation. If you do the calculation, you're going to end up with such an expression, right? You're going to end up with, by having this, oh, sorry. This should be xt. Sorry. This is a typo. No. This one should be xt. So you are going to have xt minus 1 in terms of xt, and your score function, and the other thing. So as you see here, the only thing that is showing up is, again, alpha for you, right? So you only need to know this alpha. This is exactly the alpha that you use when you wanted to move forward, right? This is exactly that one, plus this score, right? This is the thing that you need. Now, we talked about it right today, so when I prepared these slides, I assumed that the lecture has been over by the previous section. So I am here to recap again. But I already did the recap for you. So this is why I have this again here. But it doesn't harm if we just look at it once again. So when we want to move backward, every time we would say, OK, we essentially need this score. So if you want to compute this score you can approximate it by the noise process divided by the variance of the noise, right? Or standard deviation of the noise, right? So this is one approach that we had. If you take this, you're going to get one computational model, one neural network. You train with these samples, and this is going to give you an estimate of the score. Or you are going to use the denoising approach, right? You would say, OK, every single time I am trying to denoise xt minus 1. OK, it has its own coefficient. I don't care. Given the xt that I have, so I get a denoiser minus the original noisy version divided by the noise variance. This is the estimate of the score. So I'm going to replace it into this score term, and I see how it goes backward, right? So that was the idea that we did in the previous session eventually, right? But the point here is that at this point of time, people tried a lot, right? They use either of these approaches. One thing that they started to see is that even if you just make the network extremely complex, like for example, if you look at your assignment, you're going to see that you have one VAE, which is quite simple encoder-decoder, and you can sample from fashion MNIST. But then when you want to just sample from MNIST only digit 8, and you want to use this approach, you're going to make much more complicated network. It's still not doing the perfect job. So people started to say, okay, maybe this is the issue, so we need to just make the network more complex so that it can grasp the idea of or it can grasp something about the data distribution. But it was always hard to make it, right? And even though people see that this is happening, like in your assignment, you see it there, but the issue is that it's not really working easily as, for example, VAE would work, right? So at some point, people started to conclude that this is not eventually the only issue. So it's not only about like you don't have perfect score network and you don't find the exact twist how you can train your network. The issue is a bit further more than that. So one obvious thing is that at the end of the day, when we are doing this process, even if we do it a long, long time forward, I mean, adding too much noise, and then we train our network on all of those samples, and having so much samples, we're going to get good network, good data set, which helps us train our network properly. But the point is that the samples that we have are extremely noisy, right? Each time that I'm estimating the score, I'm just taking that error term divided by the standard deviation, right? And that term, even though that is unbiased estimator, this is still very noisy, right? So I need to increase my number of samples hugely large so that this variance starts to shrink, right? So this is one point that you see. And the other thing is that the score itself that you want to learn, that is a quite complicated thing because it has most of the distribution inside it, right? So you eventually, when you are computing score, you have the distribution up to a constant, right? This means that the score itself is a complicated function, and a simple network cannot do it. But from variational autoencoder or GANs, we do know that we should not really need this huge network, right? So there are always easier approaches to generate data because data is always lying in a very tiny manifold, right, in the latent space. Now, the other thing that people started to notice, and when I say started to notice, time-wise, they actually noticed afterward because the other approach was already out, then people started to connect it to SDE. But anyways, if we just follow the logic way of things coming out. The other thing was that this trajectory that we are writing down in order to just find out the way, the reverse trajectory from noise, the latent variable, into the data, this guy itself is coming by an SDE, right? And that SDE is, I mean, we cannot really solve it. We are just approximating that one, right? So if you remember when we started to write down those Markov chains, what did we do? I told you that, okay, we assume that the time difference, like between one step to another, is a tiny bit, right? And then I would say, okay, the location at the next time is pretty much the location in the previous time plus d, the difference in the location, right? Computed by that SDE, correct? And then we put that dx inside on the other side of the equation, inside this expression to end up with that Markov chain, right? But that is not an accurate approach, right? If you want to be more accurate, you need to write down like the x at the tiny bit of time next is going to be the original x plus d of x plus half d squared plus 1/3 factorial third derivative, and so on, right? So if you want to be accurate in terms of this approximation, you need to have the higher order derivatives, right? Now, you might ask me two things. The first one is that, okay, I have dx, right, equals to something inside SDE. Why can't I just compute d2? I just take derivative from both sides, right? This should be d2, right? Everybody's clear what I'm saying? So in the SDE, we have this dxt equals to something, right? If I need the next derivative, so I'm going to get the derivative of both sides, right? That should work. But that you cannot do it. Do you know why? Any guess? You do know, you do have the expression. I mean, that's given by the, for example, Langevin dynamics, or the one which I showed you, right? We always write down one forward diffusion, right? So I have that forward diffusion, but I cannot take the derivative. Any idea why? So when the SDE expression, you have it always in this form. So it's going to be one drift term, f dt, plus you have something else, g, times, what is it here? D of? No, gradient of log is here again. You're right, but this is in the drift. Here, what do I have then? The Brownian motion, right? You remember that, right? Now, this Brownian motion, it does not have further derivatives. Okay? So you cannot do it. You cannot take derivative of this guy. It's not differentiable because it's a random process. Okay? You cannot do it. Yeah? And you can simply go ahead, check this term. E-tool, calculus. If you're interested. To know that people started to develop approaches for taking derivative of this guy, but you cannot go more than one order. Okay? So the point is that you have Brownian motion. You cannot take higher derivative. This is not possible for us. It's not a simple equation where everything there is an explicit term that you can take the derivative, right? This is not possible. This is one thing. And the other thing is that those terms, even though we don't know this guy, but we can guess that this other term, d squared, this one, could be very large, right? Because this is coming out of the derivative of a random process, right? And that random process is not controlled by us. I mean, this is not a nice function going like this, which I say, okay, the second derivative is small enough that I can ignore, right? So the Brownian motion could just behave extremely up and down, right? So those terms, these terms that you have here, they could eventually be very large. And if they are very large, even if you make your time step extremely small, still the approximation that you get is totally nonsense. Okay? So the main reason, to my understanding, and this is a part of it is my understanding because I couldn't find it anywhere else, but my understanding is that the main reason that when you go directly by approximating SDE or physical diffusion, you do not end up with a good model or a good kind of generation mechanism. The main reason is this guy. The main reason is that you have an approximation which is not exact, and not only it's not exact, you cannot say that it's good enough. There is no guarantee that this is good enough. It could be extremely different from your original SDE. Okay? So, moral of the story, that SDE, even though that is nice, even though that inspires us to just go for diffusion process, that is not something that really at the end of the day is able to generate the data.